Fantastic. So the next speaker of this session is Leonardo Banchi from the University of Florence in Italy, and he will be talking about quantum barcode decoding and pattern recognition. Over to you, Leonardo.
Thank you. So I hope everybody can hear me. So it's a great pleasure to be here, and I want to thank the organizers for this great conference. So here indeed I'll talk about quantum barcode decoding and pattern recognition. So my so my talk is organized as follows. So I'll first discuss about the problem of barcode decoding, which is a kind of multi-target version of quantum illumination and quantum radars, so to speak. But possibly with a non-uniform prior. And then I will discuss what happens when we don't know the prior, and somehow we must learn it from, and we must learn our decoding protocol from the data, as in supervised learning. So the first two topics here deal with the optimization of quantum sensors for discrimination. The last topic, on the other hand, is a more theoretical topic. So it deals with that question. So when do quantum models generalize? So of course, one can check generalization by studying the testing error, namely see how the trained model performs with the unseen data from what is called the testing set. But here, on the other hand, I will take a more formal approach, somehow showing how to study generalization using tools from quantum information theory. Okay, so we first study whether we may expect some advantages in using quantum sensors and entangled photonic states for decoding barcodes. So here, what I call a barcode is something like this for 1D and this for a 2D barcode. So it's basically an image whose pixels can only have two possible colors, so either black or white. So from the physical point of view, each color here corresponds to a quantum channel that scatters light in a different way, for instance, with a different wavelength and other things. So in our notation, so this I here represents the value of all the binary pixels in the barcode, and for instance, rho of I is the quantum state seen by the detector. So for optimal detection, we need maybe something like this. So we need possibly some entangled inputs, and some modes for the entangled inputs are sent to the channels, others are kept in others. Then we use, let's say, an optical circuit to mix all of these modes together, and then we perform a measurement described by a POVM. And then after the POVM, we may also add some classical post-processing routines. So, so one can show that if you optimize over the whole of this measurement part, so the minimum probability of wrong classification, so namely the probability of not perfectly detecting all the pixels, is upper bounded by this quantity here, which depends on the fidelity. Which depends on the fidelity between different quantum states. So here Fij is the fidelity for two states, rho I and rho j. So pi I is, on the other hand, the prior probability to get a certain image, and which may be possibly unknown. And m here is the number of probes. So for both classical and quantum inputs, one can calculate all of these fidelities, and then one can bound the classification error. So we will claim here that guaranteed quantum advantage, so whenever the upper bound here that we get using quantum inputs is smaller than the lower bound here that we get using coherent states. So moreover, we have also asymptotically shown, where here asymptotically means for large M, that the upper bound here can be achieved by a strategy like this. So namely, when you use local measurements. And this is important because local measurements are easier to perform experimentally. Okay, so as a first study, so we compare the performance, as I said, with either true mode squeeze vacuum input states or coherent input states. And we use the same average number of photons in both cases. So in this example, so each pixel is modeled as a bosonic channel with a transmissivity eta I, where I is either black or white. So we have shown that guaranteed quantum advantage is always possible for large M, large number of probes. So whenever this quantity null threshold, which is also displayed here, is positive. So more precisely, so this quantum advantage can be obtained when this inequality is satisfied, where small m here is the number of pixels in the barcode. And you can also see from this image on the right that null threshold is positive in this area, so in the top right corner. And the maximum value is obtained either here or here, so where you also get the maximum quantum advantage. So basically when one of the true transmissivities is close to 1, and the other one is quite low, like around 0.2, as you see here. So this is a slice of the picture here. Then we have also studied a different model with what is the so-called thermal images, where each pixel is defined as a Gaussian phase insensitive channel. And here the different colors have the identical transmissivities, tau, but different environmental noise. And so also here, quantum advantage can be obtained for large M. So when the number of probes is sufficiently large, so larger than this quantity here. And this quantity here, I mean, it depends on all the parameters for the two channels. So here there are some examples where you can see that, so when tau is larger than 0.95, somehow this quantity is finite. So I won't discuss all the figures here because of the lack of time, but you can find all the details in this paper here on the archive. Then finally, we have also studied the advantage of using a different quantum input, let's say without idlers. So you remember here in this picture that, so here we used, previously we used true mode squeeze vacuum states, where somehow one mode was sent to the channel and the other one was kept with the idlers. And one can prove that these inputs are optimal for teleportation covariant channels, but experimentally somehow it is difficult sometimes to do these idlers. So we have also studied a different approach where somehow we use a multi-mode entangled state, like a bosonic version of the G8Z state. And so as we see in these numerical figures, so even in this case, there are regions in the parameter space that for which one can get quantum advantage. Okay, let me now go to the second part of the talk, which is about pattern recognition. So we have proven that physical pattern recognition tasks, such as using light to perform handwriting recognition, so we have shown that this is significantly simpler than the barcode decoding because somehow errors are tolerated. Indeed, a human eye can immediately recognize that all these characters here and here, a human eye can also detect even these numbers even when some pixels are randomly flipped. That's because somehow, so we were able to detect these patterns. So we were able to formally show this, namely that this pattern recognition problem is easier because these errors are tolerated by studying somehow bounds on the training error, which is what I called here the EQ. And the bounds depend on the fidelity between the true states that describe either black and white pixels, but to the power of m, which is again the number of probes, and this h mean, which is the minimum Hamming distance between images from different classes. So the Hamming distance is somehow the number of pixels that you have to flip to turn this 4 into this 9. And so for the MNIST dataset, so it turns out that the Hamming distances between images from different classes, so they follow a kind of, I mean, pretty well this sort of Gaussian distribution. And from this distribution, one can also check that the minimum Hamming distance is around 30. This is for the for the MNIST dataset. So then, so now going back to this inequality, so T here is the size of the training set. So using these bounds on the training error, then we have shown that somehow guaranteed quantum advantage is possible when the number of probes is large enough. So it's larger than a certain quantity that depends on the minimum Hamming distance between images, the number of training samples, which is this T, and this new threshold quantity that depends on the properties of the bosonic channel. So this numerical value here on the right is for the MNIST dataset, and the new threshold is the quantity that we studied, for instance, in this picture here. Then we have also studied a simpler experiment for near-term hardware. So for instance, using single pixel detection followed by a very simple nearest neighbor classifier, which is remarkably stable against error. And this is because somehow the Hamming distance between images from different classes is relatively large. So you have to wrongly detect many pixels before getting somehow the wrong classification. This is the idea. And again, all of these bounds are for the optimal POVM, and you can see the bounds here where you can see the quantum advantage. But we have also studied what happens with photo detection measurements, which are these yellow and light blue curves. And because photo detection somehow are done also in many experiments nowadays. So even with photo detection, which is in general non-optimal, we have observed that quantum entangled inputs allows us to get a better classification accuracy, as you can see from these curves. Then we have also considered a more advanced classical post-processing using convolutional neural networks. So basically the outcomes from an array of detectors is fed onto a convolutional neural network, which is then optimized to get the right classification. So you see from these plots here that convolutional neural networks are always better than the very simple nearest neighbor classifier, basically no regimes, and that the classification error decreases also as a function so for larger training sets. So all the details again can be seen in this paper. Now, let me jump then to the final part of the talk, which deals with a more theoretical question. So we have seen how to bound the performance of the different classifiers, and what you have seen in my plots, in the plots is basically the training error. So the average classification error over the training set after the optimization. But the most important aspect in machine learning is the generalization. What can we say about generalization? So here then we have studied, let's say, a more general theory. So the theory here applies more generally, so not just for classifying physical images via quantum sensors. So it can be applied whenever we have a quantum state, rho of x, that depends on some quantity or some property x that we want to classify via some POVM, whose outcome is the class. And we do this we learn this classification via, let's say, a collection of correctly classified images. So for instance, the way x is mapped into this rho x is what I here call the quantum embedding. And the models studied before are examples of embeddings onto bosonic Gaussian states. Now, suppose that we have a training set made of T correctly classified images, like the MNIST on the right, and we can empirically check the generalization by computing the testing error over the testing set. But if we fix the embedding and we optimize over all the measurements, then the theoretical question is what training error and testing error can we expect? Now, I don't have time to properly introduce all the mathematical notation because I have just a few minutes, but you can find all the details in this paper, here. Okay, so one of the most important results is the study of the generalization as a function of the quantum embedding complexity. Now, you may expect that with whatever notion of complexity, so this classification error, which is this red curve here, should decrease with more complex models. So for instance, models with more parameters to train. And the training error indeed also shows the same trend of this red curve here, so it decreases. Now, the theoretical minimum error that can be achieved by any statistical argument is the bias risk. And the difference between the red curve and the bias risk, which is this A quantity here, is what is called the approximation error, which depends on the embedding. So if you have an infinite amount of training data, this is the error you will get. But on the other hand, the average testing error, which is this light blue curve, is basically the average loss with the classifier built from data from the training set. So it cannot be smaller than the classification error. And the difference between the light blue and the red curves is this G quantity here, which is the generalization error. So the generalization error somehow studies how the data-driven classifier performs with unseen data. So for models of moderate complexity, we know that the generalization error is expected to increase with the complexity of the model after a while. So because of overfitting. So we won't study here what happens in the deep learning-like regime, where models with, let's say, many hundreds of millions of parameters are able to both have low training and low testing error. So this is still an open question we are working on. So now let me jump to the main theoretical result here, is that, so we have shown that the generalization error is bounded by this B quantity divided by the number of training samples. So this is a Rademacher-like generalization bound for those who know what I'm talking about, while the approximation error somehow depends on properties of the average and encoded states. So both the quantities entering in the generalization and approximation errors can be expressed using entropies, like here. And the B quantity in the generalization bound depends on the mutual information between the quantum embedding and the classical input space, while the approximation error depends on the mutual information between the quantum embedding and the class space. So all the entropies here are defined for this classical quantum state, where Q somehow refers to the quantum embedding, and C and X are classical spaces. Now, this is my last technical slide. So from our quantities, then we can also study some geometrical bounds that links somehow the approximation and generalization error to the fidelity between quantum embeddings, which was extensively studied in our theoretical results for theoretical analysis for barcode decoding and pattern recognition. So, and according to this analysis, a good embedding should cluster data from the same class into nearby points of the Hilbert space and separate as much as possible different points from different classes, as we see in this picture. We have also studied many other properties in this paper, but even also for other forms of quantum classifiers, but I don't have time to discuss them here. We have also shown a link between the information bottleneck and this generalization approximation results. But again, I don't have time because I'm running out of time. So let me now jump to the conclusions. So we have studied quantum enhanced sensors, and we have shown that quantum enhanced sensors allow better image and pattern recognition. We have shown that photon counting experiments plus some classical post-processing, for instance, based on neural networks, can be used to demonstrate such a quantum advantage. And this quantum advantage can be achieved either with inputs and made with idlers, so for instance, true mode, squeeze vacuum, plus this sort of quantum memory, or like via idler-free states, like a bosonic version of the GHZ state. And then we studied a more theoretical question of generalization in quantum machine learning, and we have shown how this can be linked to entropic quantities. So we have drawn many conclusions from these links. So one very simple one is that the link between good generalization and trading that can be studied when the fidelity between two states is small, if the inputs are from different classes, and high if the inputs are from the same class. So with this, I thank you very much for your attention.
Awesome, thank you very much, Leonardo. That was a very interesting talk, and I think it's moving firmly closer to data processing and kind of some of the machine learning concepts. We have a few minutes for questions. What I see in the chat is what is TMSV? And I can answer what the acronym stands for. That's two-mode squeezed vacuum, but I suspect there'll be people in the audience who don't have a quantum optics background. So I'm wondering whether you want to explain slightly what that means.
Right. So the two-mode, I mean, in a very simple term, this two-mode squeezed vacuum state is very similar to like it's like a finite energy approximation of a Bell state. So it can be obtained by a, let's say, two-mode squeezing operator applied to the vacuum, and so the sim is like a finite energy approximation to a maximally entangled state, so to speak. Very naively speaking. I don't know if that's a very short answer for.
Maybe let's leave it there for now. Thanks, Leonardo. Let's see. Oh, yeah, there's a thank you from the person who posted the question, and I suppose there's opportunities on Slack to delve deeper. I had one which is a slightly sort of broader picture question, perhaps, which is, so you're talking about the quantum probes have an advantage, and then there was kind of the neural. Actually, you have it here on this slide. You have the classical post-processing, which looks like a sort of neural network structure. So one question that I had is that two separate tools that help, but in some sense they don't have much to do with each other? Or is it the case that when you use quantum probes, the data becomes harder to process, and it's more important to kind of get the classical data, the classical post-processing right, and use clever machine learning approaches or inference-based approaches? I'm wondering whether you'd like to comment on that.
Thanks very much for the question. I think it's a hard question because I don't know exactly the answer. So here we considered two approaches. Mm-hmm. One approach was like to bound somehow the best thing you can do, let's say by optimizing over all of these things. And this would, I mean, we could bound this using the formalism of POVMs. Mm-hmm. So in that case, let's say we have the true optimum here. So the second approach, but somehow using this bound, sometimes you don't know how to construct such optimal measurement. Mm-hmm. And so the second part, we said, okay, so we don't know how to construct this optimal measurement. Let's try to use like some measurements that can be done even nowadays, or that are simple enough. And then let's try to somehow use after this measurement some selections, so some classical post-processing part, in order to extract the information from these measurements. So that's what we have done. Somehow, so the second part here is more like, so it might not be, so the optimum, it can also be obtained via, let's say, the most clever quantum measurement you can devise. Mm. But let's say this is more like a near-term version of like a non-optimal measurement. Okay. So it's something to construct a non-optimal measurements based on what the possible detectors that are available.
Indeed, yes, excellent. I appreciate it. It's a hard question. I think the clock's up against us. I think we need to move on. But thanks a lot for a beautiful talk, Leonardo.
Okay, thank you. So I stopped sharing.
Yeah, if you stop sharing, and David, when you're ready, would you like to share and put your slides up? Hi, David.
Hi. Yeah, let me try.
I can see them.
You can see them? Okay,
they're not full screen yet, but I can see them.
Okay, great. And now?
Yes, indeed. I think you're set to go. Fantastic. So the final speaker of this session is David Wise from University College London. And David's talking about a neural network-based approach to efficient inference of the qubit noise environment. Fantastic. Thanks, David. Over to you.
Great. Thank you very much for having me. This is some work that I've been doing with my supervisor, John Morton, and a postdoc in our group, Siddharth Domka, who's really the brains of the operation in this. So let me just begin by going through what I'm going to talk about. So I'm going to start with just a brief introduction to qubits and decoherence. So we're all hopefully on vaguely the same page. Talk a bit about how decoherence relates to the noise spectra that qubits can experience. And then I'm going to talk about how we can go about actually extracting the noise spectrum that a qubit experiences and some of the ways we can do that. So the first of these is what I call a delta function approach. So this is a sort of a traditional and fairly simple technique. And then I'll talk about a more advanced way of doing this. And these are both sort of traditional non-deep learning approaches. Next one I'm going to talk about is the method that we've developed and to try and tackle this problem, which is a deep learning approach. I'll run through just a few details on our training data generation and then look at our results for monotonic noise spectra and for non-monotonic noise spectra. Finally, I'll look at a bit of how this is done practically, how we think it can be applied experimentally, and what we're trying to improve. So just to sort of go over the problem that we're trying to solve. So qubits experience noise, and this noise often affects them in terms of their coherence. So coherence is just a measure effectively of how long a qubit will keep its quantum state for. So the noise that a qubit experiences, it might be something we want to get rid of. So if you're talking in a quantum computing context, this noise might be really annoying and you just want to get rid of it. But if you can understand it better, then that might help you to develop either pulse sequences or protocols that really allow you to minimize that. Or maybe more relevant for this conference, that noise might be something you want to understand better. In the case of quantum sensing, we heard in Christian's talk earlier that these, what looks like noise can actually reveal a huge amount about the environment the qubit's in. So just quickly, what is decoherence? So as a simple explanation, it's the process that causes a qubit to lose its quantum state. So if we look at these spheres on the right, this is the block sphere. But if you have a qubit starting at the kind of north pole of the sphere, and then you use what's called a pi/2 pulse, a 90-degree pulse, to put it into the XY plane of this sphere, you've created a superposition state, and this is now a kind of quantum state. Over time, this state will kind of lose its quantum nature and decay into something classical. And if you just leave it alone, that'll happen very quickly. But we can use these pulse sequences, so like the one above, we can flip the qubit, and then actually the processes that cause it to decay, its quantum state to decay, kind of happen in reverse, and it returns that quantum state. Now this pulse sequence we see above is fine in the case of static effects on the qubit, and it will reverse those fine. But in most cases, qubits are actually experiencing, and we saw this earlier, noise that covers a huge spectrum, so it's changing over time. And we can see that as it changes over time, this sequence isn't going to reverse it. And as this sequence gets longer, the qubit's going to have less and less quantum nature to it. And that's called the process of decoherence. And the graph at the bottom is really just showing this very simply. If you start with a kind of coherence of 1, and you gradually extend how long you let the qubits sit in a superposition for, that coherence is going to decay from 1 to 0 over time. What we're also seeing is you can actually change this pulse sequence to better protect your qubit from the environment. So this is if you have a 4 pi pulse instead of a 1 pi pulse sequence, this is a sort of CPMG sequence, then you can actually extend your coherence from sort of a 1 millisecond time to a 4 millisecond time. And that will make it last long. So how does this relate to kind of noise and the noise spectrum? So these pulse sequences that we talked about, they can actually be described by something called a filter function. And what that filter function describes, and you can see a couple of examples in the top right here, is how exposed a qubit is to noise at a given frequency. So you can see here that this qubit, in this case, for this pulse sequence, would be exposed to noise at this kind of 2 × 10⁶ radian per second region, this big peak. And then there are these higher harmonics as well. What we're also seeing is the filter functions will change based on the pulse sequence you use. So as you add pulses, these filters get narrower and sort of taller. Now, if you have a noise spectrum, the convolution between the filter function and the noise spectrum will actually give you how the qubit decays. And that's based on this kind of equation on the bottom left, which is an instance of called the Friedholm equation. But effectively, all it's saying is that the logarithm of the coherence decay, CFT, is proportional to the integral of this noise spectrum times this filter function. And if you have your noise spectrum and your filter function, you can get the coherence decay easily. Now, the filter function is easy to derive. There's a fairly simple equation that goes from your pulse sequence timings and lengths. That's easy to get. The coherence decay is something we measure frequently in labs. This is not a problematic thing to get. So what we'd really like is the S of omega here, which is the noise spectrum. Now, sadly, that's a less easy problem to solve. So starting with a filter function and a coherence decay, this equation isn't actually easily solvable. So you have to introduce some extra methods if you want to go from a coherence measurement and a filter function to deriving this noise spectrum. So how can you do that? The first step that people usually use is a mathematical approximation. And if you treat these peaks in the filter function actually as a delta function, you get this very simple relationship between the coherence decay and your S of omega. So this just minus pi log of the coherence divided by time. And that's great. So that's an easy relationship, but it's not a particularly accurate one. So what these graphs are showing on below is S actual is the underlying noise spectrum. The coherence decays above are derived from that noise spectrum based on the pulse sequences used. And then the orange and blue noise spectra are derived using this delta function approximation. So it does pretty well. It's in the right ballpark, but it's not especially accurate, and it's probably not going to give us enough information to really understand what the environment's doing. But it's a good starting point. There are quite a few alternative methods for doing this better, but they tend to be significantly more taxing experimentally. So one of these is what I've termed the Alvarez-Suter approach. We've looked at this in more detail in a recent paper, but at a fundamental level, what it does is instead of taking a single measurement of coherence, it takes multiple measurements of coherence. And instead of using a single pulse sequence and changing the times of that pulse sequence, what it does is it keeps a fixed tau, so that's the gap between the pi pulses, and actually just adds more pi pulses. And that's how that decay will give you effectively 1 point in your noise spectrum curve. And if you repeat this multiple times, so multiple pulse sequences with different values of tau, you can actually derive a pretty accurate noise spectrum. The problem with this, of course, is that to achieve good resolution, you need to be repeating your experiment multiple times, but it does very well. So the question we had is, could we do something similar? Could we try and go from a coherence decay and get a noise spectrum out using neural networks? So, as I'm sure people have heard, neural networks can be considered universal function approximators. So it seems natural to think that they might be able to kind of invert this Friedholm equation if they're powerful enough. So the nice thing is we can actually leverage the way that the Friedholm equation is easily solvable in one direction to generate the sort of large amounts of training data that these neural networks typically need to work well. So because it's easy to go from S of omega to C of t, we can generate underlying noise spectra based on what we know about typical noise backgrounds of typical qubits. So those tend to have either a sort of 1/f type noise or a Lorentzian type noise. We can simulate those based on kind of understood parameters, simulate a range of those, and then derive the coherence decays that are associated with them. What we then can do is take this coherence decay as the input to a neural network with the corresponding noise spectrum as the target of that neural network. And then train the network in a standard way, in a sort of regression style problem rather than a classification style problem, to see if it can output that noise spectrum. We've looked at mainly LSTM type networks for this. we looked at a few different ones, but most of our results and all the results I'll show here are with LSTMs, based on sort of reading around and understanding they're quite good for this time series type data. We've also begun to look at convolutional autoencoders, which we think are probably going to be the most useful thing to move forward with. So firstly, I just wanted to show you some results versus the delta function. So this is taking its most basic approach. And what I say here is just a histogram of errors across 3 different types of noise, so Lorentzian, 1/f, and stretched exponential. And we can see that the delta function does, as we expect, between sort of 8% error and about 50% error. Now, for a single neural network trained on all 3 of these noise spectra, it can do significantly better. So we actually had a mean error in this case of about 0.1%. You can probably improve that, but given that we want to look at how this works for the experiment, that's significantly below what we'd expect as an experimental noise force. So we're not sure that you want to do much better than this. You can just see on the right some examples of how that looks in terms of the reconstructed noise spectra. So you can see actually this neural network approach seems to work very well and works well in comparison to this delta function. So we then applied it to a few sort of special cases. So firstly, one of the limitations with this approach is that we're kind of having to assume an implicit time vector in the coherence decay we're inputting. So on the left, A and B, we have just used a shorter time vector, trained it on that to make sure we can look at a range of coherence decays. And once again, although this is only for one case, so you would anticipate the performance to be a little worse once it was trained, having to recognize multiple noise forms. The stretched exponential, the neural network approach does pretty well, similarly to before. Secondly, in C and D, we looked at if you take a more complex noise form, so something with sum of 2 Lorentzians in there, so what we call the double Lorentzian. So this is obviously a more complex form of noise, and you can see that once again the delta function is performing similarly, and the neural network approach is definitely struggling a bit more, but again seemingly outperforming the delta function approach quite significantly with a mean error of about 0.5%. Finally, we actually looked at how the delta function performs when you're using a 32 pi pulse sequence to generate your coherence decay. So everything else is generated with a simple Hahn echo, so that's just a single pi pulse. But realistically, experimentally, it's not significantly more challenging to do a CPMG sequence. Actually, in this case, it turns out that the delta function approximation doesn't do significantly better, and in fact does worse in some cases, whilst the neural network approach does similarly well. So that actually was, I mean, a surprise for us. We thought that, you know, as you increase the number of pulses, the filter function would become more delta function-like. But we think probably the contribution of the higher harmonics is having an effect here. So this shows that the neural network is definitely significantly outperforming the delta function approach. But what we wanted to look at then was how it did against a much more advanced technique, so this Alvarez-Suter approach. In this case, we also looked at a more complex form of noise spectrum, so what we call a non-monotonic noise spectrum. So you can see that on the bottom right, that you have this noise spectrum that has a kind of a peak, which is not centered at 0. And that's associated typically with interaction with some sort of spin species. So if you're looking earlier, the NV center interacting with carbon-13s, you might expect to see a peak like this centered at the carbon-13 frequency. So you can see here that the Alvarez-Suter model does extremely well. It had a mean error of about 4 to 5%, a very short tail. The neural network approach actually does really pretty well on this as well. We had a mean error of about 2.5%, but with a slightly longer tail. So our sort of max error in this case was around 20 to 25%. But it's nice to see that this approach is comparable to this state-of-the-art approach, which requires significantly more experimental input in order to get your results out. So lastly, we wanted to look at how you're actually going to work with experimental data. So everything we've used so far is inputting smooth curves into the neural networks. If you look at the bottom left, this is just an example of simulated noise in these coherence decays. So in this case, plus minus 5%. And we actually thought the first thing you think is, well, we can fit to it with a stretched exponential to get a smooth curve to input into our neural network. The problem we have there is that you're kind of assuming an underlying structure to the data and assuming an underlying noise spectrum. So what we've done instead is looked at if we can do better with, again, a neural network sort of smoothing based approach. And you can see that this is the histogram of errors. We're actually looking at the log of the errors rather than just the base errors, because that's, if you remember the Freedom equation, that it's log C of t that's proportional to the noise spectrum rather than just C of t. And we can see here that actually the neural network does pretty much the same for 4 coherence decays derived from 4 different types of noise. The curve fitting approach actually does really poorly in this double Lorentzian and Lorentzian case, which we think is probably due to the stretched exponential fitting really not being an appropriate fitting approach for the derived coherence decay. So that's kind of where we've got to so far. Our next steps are, well, firstly, in sort of experimental validation of this work. So we're starting to get back into our labs, which is nice. So we're hopefully not too far away from getting some results actually demonstrating that this works in the real world. We really want to work with broader data sets, and convolutional autoencoders we think are helping with this. But particularly we're looking at this from a very kind of spin perspective, because this is our expertise in the lab. So we're very interested to try and understand what the noise spectra of different forms of qubits might be. So that might be superconducting or quantum dots. We also want to look at a better way of working with noisy data. So it's a slightly inelegant solution to have to use a smoothing network. We want to see if we can do it with just a single network. Partly what we think might help is if you have multiple pulse sequence inputs. So instead of a single coherence decay that you average 100 times to get rid of as much noise as you can, if you instead did a Hahn-Echo decay and a CPMG, say 32 pi pulse sequence, and you average those 50 each, is that going to give you more information without a huge extra input of experimental resources? So if anyone was interested in anything I had to say and would like to know more, we've just released this paper in PRX Quantum. Anyone wanting to chat to me about it, please do. I'd love to hear more. And that's that. Thank you very much.
Great, thank you very much, David. Beautifully timed as well. We've got a few minutes for questions. I have a couple. I don't see any at the moment in the Q&A window, so I'd encourage people in the audience, please feel free to post. It's not too late. David, one thing I was wondering about, and I think you began to kind of discuss it and answer it possibly, but when you tried the delta function approach and it failed, it seemed to do reasonably well in one part of the plot, and then you're going from right to left, you kind of climb up, and it plateaued very differently. Do you have more of an understanding, I guess, why does it fail? And I think you've maybe started talking about it. And how do you know? Can you predict where along the x-axis it fails? So is there a way of fixing it? Maybe you have no reason because your alternative approach works so well, but just out of curiosity.
No, that is a really a good question. I'm sorry to say I don't have the exact answer to it. It's definitely, I think it's something that we should look at more, because obviously if we can work out a simple, just kind of approach to, we can tweak the delta function. Yeah. We think partly looking at how these sequences behave, it tends to be that, so certainly some exploration we've done with multiple sequences, as you use, say, a CPMG sequence, that tends to give you more information about the high frequency of the noise spectrum. And as we use, obviously, the fewer pi pulses, you tend to get more information about the lower range. but actually we haven't really examined it in the same way with the delta function. So it would be definitely an interesting thought to see if as you change that, does that change the position on the x-axis?
I think that's a bit related, right? I was wondering, how can you change the filter function? And you said it's you tried, but it's the higher harmonics that spoil things and can make it worse. But I guess if you know what causes the problem, is there something that's a bit more sophisticated than your delta approximation, but doesn't really need the machinery of the neural network? I know we had machine learning for quantum, so the machine learning probably is the way forward. It's kind of, again, just thinking, so definitely. So actually, the solutions fail.
So I think that's another area that we want to explore. So there's actually, you can kind of engineer your filter function with your pulse sequence to be more delta function-like. So that's definitely an alternative approach. We, again, I think, need to understand this better, and it's something we're looking into. I don't have the citations on me now, but in our paper we talk about it a bit, that there are these much more sophisticated pulse sequences which are designed to make the filter function delta function-like and really improve this approximation. Exactly.
Okay, thanks for that. There is a question here. Yes, I'll read that out. Thanks for your talk. Regarding the comparison with the Alvarez-Suter method, did you choose 32 pulses for some specific reason? Have you tried with different number of pulses?
So actually, in this case, for the Alvarez-Suter method, both were compared on Hahn echoes. So no, we are in the process of looking at. So the Hahn echo we chose just because it's the sort of simplest starting point experimentally, and that seemed natural to us as experimentalists. But I think there's definitely a good reason to explore alternatives and see, does this perform much better with other approaches? Obviously, the Alvarez-Suter method is using this more complex sequence where you're kind of adding pi pulses each time. So it's kind of fundamentally a different way of doing things.
Okay, thanks. Maybe final question from me before we wrap up the session. So I was wondering, I guess, is there a better way to make use, or are you making use of the prior information? Presumably in an experimental situation, you know what sort of noise spectrum you're going to get, where you have a clear expectation what it should look like. I guess that's prior information. I know you're modeling them, but does that help you? Can you combine that in the neural network approach? Can you make use of that prior information? And add a second part to it, and I think you also touched on it, right? How do you find the optimal settings? But maybe that's kind of future work. How do you find the optimal? How do you go about identifying the optimal pulse sequence? And that sounds like another possibly machine learning problem, but I don't know.
Yeah, no, that's a good question. So your first part, the priors, obviously these networks do the kind of less restricted the more restricted your noise spectral forms are, the better they perform. So you can use that in a very kind of crude way. You can say, oh, well, I'm expecting this kind of qubit to have this kind of noise. So you can restrict the training to that. It would definitely be useful, and I think the sort of making judgments based on prior information would be useful for actually trying to estimate the error of our predictions, which is something we're really looking into, because what you don't want is the network spits out something that you kind of trust and actually turns out to be complete nonsense. So I think trying to use this prior information to make judgments on what the error might be of our predictions is really important. In terms of optimal sequences, we looked at a couple of things. So we did some simple work with just some very standard optimization of moving pulses around and seeing how much better you can do than a CPMG or an Uric decoupling sequence by optimizing to the noise spectrum. And we got some quite nice results with some standard approaches. We then are looking a little bit at deep learning to see if you can do something to optimize with deep learning. At the moment, we're doing much worse than the kind of much more boring approaches, but that probably says more about my deep learning skills than suitability of it in the first place.
Okay, thanks. So you're thinking about, yeah, pulse sequences, that's a dark art, that's black magic to me, but that's, I think looking at the clock, we need to wrap it up. Thanks a lot, David. I'd like to take the opportunity actually to thank all three speakers for this very exciting session, and apologies to everyone for overrunning by a few minutes, but now there's a break of, I believe, 1 hour and 20 minutes before it continues. So hopefully enough time for those of us in Europe to grab a quick dinner. Fantastic. Thanks everyone, and bye for now.